let's find a polynomial function p that satisfies the following. All right, so we just want to construct a polynomial function here. We're going to combine a kind of a bunch of ideas into this one problem. So let's get going. Let's take this maybe one step at a time, and we can maybe attack this piece by piece. So as x goes toward negative infinity, our function value needs to go toward infinity. So what this means, why don't we just draw a picture of what we want. So as x goes toward negative infinity, we want our function to go to positive infinity. So let's start drawing a picture. What this means here is if we go toward the left on our function, we want it to go up. So we want it to go up on the left side. All right, so next we've got the graph of y equal p of x touches the x-axis at -2, 0. So -2, 0, all right? Okay, p of 0 is 3, so that's 1, 2, 3, there it is. P of 1 is 0, so there's that. And then we have, as x goes toward negative infinity, p of x goes toward, wait a minute. As x goes toward positive infinity, that is, excuse me, our function value goes toward negative infinity. So that means as we go to the right, our function value is going to go down, so we want to go down. All right, so we want to make this as easy as possible for us. We don't want to add anything else to the function. We don't want to, make it more difficult for ourselves. We want to keep things nice and easy. So we know it's a polynomial. We know that it's continuous. So that means that we can just take and just, fill in the curve. So la-di-da, here we go, connecting the dots, and we go down at some point. Okay, so here is a picture that we can start referencing ourselves to. Okay, well, let's take a look at some of these ideas from the textbook. So we knew on page, I just printed this out here on page 240. It tells us about end behavior of our functions. So something that happened, I think probably on page 239, was that we found that the only thing that really matters when we're talking about end behavior is the degree of the leading term and the sign of the leading coefficient. So the degree of the leading term can either be even or odd, and the sign of the leading coefficient can be either positive or negative. And we've got, some options here. So the first box here, we've got n even. Well, if we're looking at strictly the graphs of these things, if we've got an even degree, our end behavior is going to be the same on both sides, right? That's essentially what these two lines are saying. For a bigger than 0, as x goes to the left, the function value goes up, so it goes up on the left. And as x goes toward infinity, the function value goes up, so it goes up on both sides. This one, same thing, similar thing. If we have a negative leading coefficient, that means both on the left and the right is going to go down. So this is not what we want. We can maybe remind ourselves real quick that we wanted opposite end behavior, right? So we can take a look at the other one. Well, this is for odd functions, and just, jumping straight to the graph, hey, these end behaviors are different. So what we're pulling out of this page is that what we need is this sort of a situation. So we have to have our leading coefficient be negative, and we also have to have the degree be odd. So from that, maybe we can just write here, we need a less than 0, and we also need an odd. So n is our degree, by the way, degree. So we need an odd degree polynomial, and we need our leading coefficient to be negative. Okay, well that's good. Okay, the graph of y equal p of x touches the x-axis at -2, 0. We've got this guy and this guy. So why didn't they write it like these? Because we could write this like this, right? So if it touches the x-axis at -2, 0, couldn't we write this as p rather? Our polynomial is p, so p of -2 has to be 0. So we've got p of -2 is 0, p of 0 is 3, p of 1 is 0. All right, so let's start constructing this thing. But first, let's take a look at the factor theorem. So the factor theorem, this is on page 258 of your textbook. So if we suppose that p is a non-zero polynomial function, which is what we've got, the real number c is a 0 of p if and only if x minus c is a factor of p. Oh boy. So the real number c is a 0 of p. So what this means, we can write this in math symbols. What that means is p of c is equal to 0. So this sentence, or excuse me, this part of the sentence, the real number c is a 0 of p, that's what this means. And hey, we've got that right there, and we've got that right there. So we have this appearing in two spots where we want it, right? Okay, so if p of c is 0, I guess there's not an if there, p of c equals 0 if and only if. So this statement, or excuse me, conjunction, is that the right word? This this phrase, I guess, would be probably general enough. If and only if. In math, this means that if and only if, this statement here is interchangeable with this one. So if and only if means that these two statements mean the same thing. So x minus c is a factor of p. That means p of c is equal to 0, and the other way around too. So if p of c is 0, then that means x minus c is a factor of p. So we can use this directly, right? We have that p of negative 2 is 0. Well, that means that x minus negative 2 has to be a factor of p. We also have that p of 1 is 0. So that means that x minus 1 has to be a factor of p. And now we can start directly constructing our polynomial. So we need to start writing this out with the nice factors. So we know we can start writing it. P of x equals, we know we have to have some number out front. Now p of negative 2 is 0. Again, from that factor theorem, that tells us that x minus negative 2 has to be a factor. And then the factor theorem tells us on this one, p minus 1 has to be, or excuse me, x minus 1 has to be a factor. Okay, that's wonderful. So what else do we need here? We don't know quite yet what this is, but we do know that we don't have an odd degree at this point, right? If we multiplied everything out, we're going to have a square. We're going to have x squared as our leading, the variable part on our leading term would be x squared. So we wanted it to be odd. Well, what are we going to do there? The multiplicity of a 0 tells us whether or not the graph touches or crosses at the x-axis. So we know that this strictly touches. So that means the degree of this piece has to be even. I didn't print out the multiplicity part, but I will reference what the page number is. Maybe I'll like put it in there or something like that, where you can find information on multiplicities. Okay, so if the graph only touches at the 0, that means it has to have even multiplicity. So we just tack a 2 up there. Okay, so now we can maybe clean this up a little bit. We've got p of x equals a times x plus 2 squared times x minus 1. Okay, so we're just about there. We just need to find out what this value of a is, right? So what we're going to use is, would it surprise you if we would use the piece we haven't used yet? So we know that p of 0 has to be 3. Well, if p of 0 is 3, that means I can put a 0 everywhere I see x, and that would have to give me 3. So if I put a 0 in for x, I'm just going to write all this stuff with the green first and then put a 0 with the red one. Okay, now if I crank that 0 through there, I'm going to have to get 3 out of the deal, right? Because that's got to be the function value. When x is 0, we have to have the function value 3, right? So put a 0 in for x, we got to get 3. So we crank a 0 through the function. Hey, it's got to be 3. So conveniently, we have that this is now an equation that must be true, so we can just solve it for a. And we can do that real quick, right? So we've got this guy is 2 squared, that's 4. We've got a -1 times 4, so that'd be -4 times a equal 3. And now we have a is equal to -3 over 4, right? We divide both sides by -4. So we have our a value, and now all we need to do is just go and plop this right there. So p of x is equal to -3/4 times x plus 2 square times x minus 1. And we have done it. So what we ought to do is we ought to check this. So what we can do to check it is just verify that all of these things are true, right? Either, maybe we have a graphing calculator, we crank it through there, and we can verify the end behavior. But what would be probably easier for you to do is verify that the 3 points that need to be there are there, and then maybe you can plug in a point that's on the other side here. But at the end of the day, we've got our nice polynomial.